All right, welcome back. We're gonna quickly go over collisions and then go ahead and go over an example to look at that more in depth. So we have a picture here that shows us a collision, a rotational, I should say an angular collision, okay, where there's some kind of angular velocity, any kind of angular motion involved. Okay, so we have in part A that a disc slides towards a stick that's motionless on a frictionless surface. Okay, and in B, after that disc hits that stick, okay, it adheres or sticks to it, and they rotate together with some omega, some angular velocity, about some pivot point. Okay, so it would be somewhere right there. It's pivoting around a nail. Okay, and in this case, we have that angular momentum is conserved for this inelastic collision because the surface is frictionless and the external force at the nail exerts no torque. Okay, so again, we're going to go ahead and look at this in closer detail in this example here. So we're going to suppose that disc that we just looked at has a mass of 50 kilograms. So I'm going to say M1 equals 50 kilograms. 50 grams. So we're going to have to convert that to kilograms, and we can go ahead and do that right now while we're thinking about it. Okay, and it has an initial velocity v of 30 meters per second when it strikes the stick that is 1.2 meters long. Okay, so it has let's see, some x. Oh, actually, since it's rotating about that stick, I'm going to go ahead and call that my radius then. 1.2 meters long with a mass of 2 kilograms. Okay, and we want to know the angular velocity of the two after the collision. Okay. So again, we're looking for the angular velocity. So what we'll do is we will use one of these equations that we just learned about. Okay, we want to use the conservation of momentum idea, okay, in order to do this. So, we know that before and after the collision, there is conservation of momentum, okay? And so this means that we'll have some I omega equals some I prime omega prime, okay? So after the collision. Okay, so before our collision, we have some initial velocity, and this was in meters per second, so it's just a linear velocity here. Okay, so we're going to have to translate that into an angular velocity, okay? And from there we can get our angular velocity after the collision, which is omega prime. Okay, so remember that our inertia is going to be our initial inertia. Let me pull this up. And we are looking at, what are we looking at here? We're looking at a disc. So the disc that we're looking at can be translated into assuming it is a point mass. So we're going to go ahead and use this inertia here, mr squared. Okay, so again, this is before the collision. So our I is going to be I can actually just write it now, mr squared. And omega, if you recall from our PowerPoint, omega is related to V in this way. So omega equals V divided by R. So I'm going to go ahead and plug that in. V divided by R. Okay. So this is this side of the equation, or L. Okay. So we get that it is mr times V. Okay. Let me see. After the collision, our inertia is not just of the disc now. Now it's the disc and the stick because they're stuck together. Okay, so we will need to add those two together. So we're going to have mr squared plus the inertia due to the stick. So we're going to go ahead and go back to here and assume that the stick is a thin rod. Okay, so we're going to say that its inertia is mr squared over 3. Okay, so let's go ahead and plug that in here. So this first one is m1, so this one is going to be m2 r squared over 3. Okay, so make sure that you see that these are different masses. So these are inertias due to different masses. Okay, so we can simplify this a little bit. m1 plus m2 over 3, both of them times r squared. So that's my I prime. Okay, so we can go ahead and equate that to this here. So we have, remember that L equals L prime. Okay, and so it's going to be mr times V, and that m is mass 1, I should note, the mass of the disk. Okay, and that should equal I prime, which is m1 plus m2 over 3 times r squared times our omega prime. Okay, so as you can see, our r crosses out with this r, one of them, and then we can go ahead and solve for omega prime. So omega prime will be m1 times V divided by m1 plus m2 divided by 3 times r. And we can plug these values in. Whoop, did not mean to do that. Not that either. Just trying to move. Okay, here we go. So our mass of the first one is 50.0 grams times 1 kilogram over 1,000 grams. Okay, times our velocity, which is 30 meters per second, divided by our masses added up. So our first mass is that 50 grams plus 2 kilograms divided by 3, and that is multiplied by our radius, which is 1.2 meters. Okay, I'm going to go ahead and do this in steps real quick. So 50 divided by 1,000 times 30, that gives me 1.5, and this is kilogram meters per second. 50 divided by 1,000 plus 2 over 3 times 1.2 gives me 0.86, and this is kilograms times meters. So then we have 1.5 divided by 0.86, and we get our angular velocity to be 1.74 radians per second. So again, this is our angular velocity after the collision. Okay? All right. Oops. Doing it again. Okay. So the second part of the problem, part B, asks what is the kinetic energy before and after the collision? So before the collision, we just have a linear velocity. So our kinetic energy is also going to be linear, okay? So it's going to be the classic 1/2 mv squared, okay? Now after the collision, our kinetic energy is going to be based on angular motion. So it's going to be 1/2 omega squared, okay? So, again, our first one is just about the disk. So it's going to be 1/2 times our mass, which is 0.05 kilograms, times our velocity, which was 30, squared. So putting that into our calculator, we get the kinetic energy was 22.5 joules. Okay, and after the collision, we have 1/2 times I prime, I should put there. So that's going to be our two masses. It's going to be the inertia of both the masses. So I'm going to go ahead and plug it in as so. So M1 is 0.05 kilograms plus 2 kilograms divided by 3, okay, times my radius, which is 1.2 meters, and that is squared. And that's going to be multiplied by my, I should put the prime there, my final angular velocity, which I just solved for as 1.74 radians per second. And again, that's squared. Okay, so I can plug everything into my calculator now. 0.05 plus 2, 3 times 1.2 squared times 1.74 squared. Okay, let me make sure that is correct. Give me 1 second here. Okay, and I get my kinetic energy after the collision is 1.56 joules. Okay, so that is my kinetic energy before and after my collision. Now, the last question is asking the total linear momentum before and after the collision. Okay, so part C is going to be the total linear, right? Linear momentum before and after the collision. So I'm going to go ahead and pause here and start another video to continue this problem.